Okay, hi. Today I am going to take a lecture about phase diagram. So, phase diagram, it is a classic graphical representation about the alloys which relates the composition of elements, and it changes under the different environmental conditions such as temperature and the pressure. Okay. So, phase diagram, it is very important to construct the alloys. Okay, so and it representing uh, amount of phases, how the phases are arranged, and it is based on the different specific composition of two different elements. Okay, so the phase diagrams are classified by unary phase diagram, binary, and tertiary phase diagram. Ternary phase diagram. Okay. In unary phase diagram, it is a normal plot, and it contains only one component or one element. And in unary phase diagram, the phase diagram plots between the pressure and the temperature. It's called a PT plot, pressure, temperature and pressure plot. Okay. So the best example for unary phase diagram is one component system of a single component system of water or iron. System, system of water and iron. Okay. So in this lecture, I'm going to talk about only the binary phase diagram, such as isomorphous phase diagram. So in binary phase diagram, this contains two elements. So in binary phase diagram, the phase diagram plot will be drawn between the composition and the temperature. Temperature and components are plays a vital role in binary phase diagram. So this binary phase diagram also classified into several ways based on the invariant reactions. Okay. So in binary phase diagram, the important thing. So for our syllabus, we discuss about only the isomer phase diagram and the erective phase diagram. Okay. So these are the important binary phase diagrams. So the so many various binary phase diagrams is there. So this important thing is the isomorphous phase diagram and erective phase diagram. In isomorphous is nothing but isomorphous means is completely soluble or completely. So in this video we are going to discuss about the isomorphous phase diagram. So in this isomorphous phase diagram, the two components are completely soluble in both the liquid and the solid state. Okay. So in isomorphous phase diagram, the two components are completely soluble. Okay. The best example for a isomorphous phase diagram is copper, nickel, and gold and silver. So in this isomorphous system, it does not produce the intermetallic and intermediate phases. Okay. So in both liquid and solid, the two compounds are completely soluble in both the states. Okay. And both are having in isomorphous phase diagram, the two elements having same crystal structures. And one more thing, the copper, nickel, and are the example for substitution of solid solution. The nickel replace the copper atoms. Okay, so both are having the same crystal structure, FCC structures. Okay, now we are going to discuss about the copper nickel phase diagram. So here's the example for isomorphous phase diagram. So in this phase diagram, in binary phase diagrams, the phase diagrams can be drawn by using the composition under the temperature. So temperature taken along x-axis and composition taken along y-axis. So the amount of copper is varies 100 to 0 along left to right. Okay, the nickel varies from right to left. So initially, the single pure copper has the melting point temperature is 1085 degrees Celsius. When we add the nickel in different values, the melting point temperature will be slowly raised and it is reached at 1483 degrees Celsius. Okay, so 1483 degrees Celsius is the melting point temperature of the pure nickel materials. So therefore, at this stage, the copper having the zero values. When we raise the temperatures, when we rise and it cooling the temperature when we changes the temperature from 100 high temperature to low temperature, the given molten alloys has been changed from liquid to solid. So when we raise the temperature above 1085 degrees Celsius, the copper or these alloys or these components changes from solid to liquids, or slowly going to or reach or is going to attain the molten state. Okay. So, so at this stage, okay. So within this range, the given components exhibit solid ranges, or they are having the both the same crystal structure. So therefore, it produces the single solid phase. Single solid phase. There is no different or differential formats, and also in liquid state, the nickel is completely dissolved in the copper atoms, or nickel is replaced the copper atom, so therefore it produces the same crystal structure in a liquid and a solid state. Okay, so in this phase diagram, additionally, the liquid plus alpha, that means the two phase will be exist within the phase diagrams. So this is the two phase diagram. So in two phase diagram, the crystal structure is also same. Okay. Okay. So therefore, in all the two states, liquid and the solid state, the two components are is completely soluble or miscible. Okay. Now, next, this phase diagram is used to find out the amount of phases present in the given alloys or given alloy systems, and it also determine the amount of components or amount of phases, how much solid will be exist within this temperature between the boundary region, or two opposite boundary regions, is also find out by the phase diagrams. Okay. Mm. So, so using phase rule, so already we will know that the phase rule gives phase rule. So F is equal to C minus P plus N. So here is 1. So therefore, there are two components in single phase region. The phase rule has been changed to F is equal to 2 minus P plus 1. Okay, is it 2? The degrees of freedom is 2. Okay. For in a, the given alloy system having one solid phase region and one liquid phase region and one two phase region. One two phase region. So at this range or at this region, the degrees of freedom of this alloy system is equal to 2 minus 2 plus 1 is equal to 1. So these are the degrees of freedom has been calculated by using the Gibbs phase rule within the phase diagrams. So when we raise the temperature from 0 to 1600 degrees Celsius, when we change the different composition or different amount of the copper and the nickel, the melting point temperature is slowly varies from 1085 degrees Celsius to 1483 degrees Celsius. Okay. Now, um, and then the amount of two-phase region is also the region or region of two-phase region will also will be changed with respect to the amount of composition present in the specific temperature and a specific composition. So, Interference, inference, inference. The phase diagram is used to determine the amount of phases and then amount of phases at a specific temperature, and next one is the composition of phases at a particular temperature. The solid will be maximum or liquid will be maximum for a specific component values. So composition of phases. So these are also find out by the phase diagrams using a tie line, and then we are going to introduce the two more parameters, that is a tie line and a lever rule. Okay. So using these two rules as tie line, two parameters, tie line and the lever rules, we are going to determine the amount of phases at a specific temperature and number of phases present, or number of sorry, the phases present within the at the specific composition or specific temperature has been calculated by this tie line and the lever rules. Okay. So let us magnify a specific region in the phase diagrams. So, so in isomorphous phase diagram, using the tie line, we are going to find out the at equilibrium condition how much amount of solid phases and how much amount of liquid phases will be present or exist at the specific temperature. Specific temperature, that means 1300 degrees Celsius, 1300 degrees Celsius. How much amount of solid present and how much amount of liquid present at the whole or the specific composition or the specific composition, how much amount of space sorry liquid phases and the solid phases will be exist within the alloy systems. Okay, is calculated by the tie lines. Okay. So tie line is nothing but is a isothermal line. We can draw a horizontal line at the horizontal line for the specific temperature. That means in this diagram, I am going to draw a horizontal line at exactly 1300 degrees Celsius. So therefore, isothermal line will be drawn between the two boundaries. Okay. So this isothermal line, it intersects the two opposite boundaries. Okay. So at this boundaries, we can draw a perpendicular line from the intersection to the composition axis. Okay. So this is called as CL, liquid composition, and this is solid composition CO, and overall composition is C naught or CO. Okay. Um, this is liquid region. Before that, this is the liquid region, and this is solid region, that is alpha region, and this is L plus alpha. So in isomorphous phase diagram, there are two boundaries there. One is the liquidus line or liquidus state. So liquidus is nothing but is a boundary between the liquid and the two phase region, and solidus is the boundary between two phase region and the solid. So next one, amount of liquid is present in the particular or specific temperature has been calculated by this formula. WL is equal to C alpha minus CO divided by C alpha minus CL. Okay, so C alpha is 43 minus 31.5 divided by, oh sorry, 43 minus 36 divided by 43 minus 31.5. So is equal to is the percentage of liquid present at the specific temperature for the whole composition. 7 by 11.5. 6 is or 67 percentage, and W alpha. So W alpha is the amount of solid phases in the region or for a specific temperature, that's 1300 degrees Celsius. So W alpha is equal to CO minus CL divided by C alpha minus CL is equal to 36 minus 31.5 divided by 43 minus 31.5. So is equal to W alpha. So W alpha is percentage of liquid and percentage of solid for the specific temperature between the two boundaries. W alpha is equal to 11.5, 33 percentage. Okay. So this tie line, we can draw a tie line for any temperature. So this tie line is used to find out the amount of phases or solid and liquid phases present at the specific temperature. Okay, using the lever rule, and tie line and lever rule also used to find out the amount of phases and composition of phases will be present at the particular specific temperature okay, for the specific region or specific components. So therefore, these are the method to determine the amount of phases present in the any two align system, which is a but in isomorphous nothing but isomorphous phase diagram. It deals with only the two solids are complete, two elements are completely soluble in both liquid and solid state. So in this diagram, both the liquid and solid has the same crystal structure. Okay, and because the nickel is completely soluble in copper solution. Okay, so in this solution, copper and nickel are completely soluble in both liquid and solid state. So therefore, it exists these they exist these the same crystalline structures. Okay, next one. Mm. So using this tie line and a lever rule, we can find out the amount of phases at for different temperatures. Different temperatures. Okay. Yeah. And then next one is the microstructure is also same for this. They're similar for all the temperatures. Okay. In copper nickel phase diagram, next we are going to discuss about microstructural changes during cooling. So in isomorphous base diagram, two compounds are exhibited the same crystalline structure. So next one is how the microstructure of these alloy has been changed with respect to cooling or reducing the temperature during reduction of temperature. How the microstructure varies with respect to the temperature has been detailed discussed in the next session. Okay, now yeah. In all the phase all in all the binary phase diagrams, the elements are, that means in copper nickel phase diagram, copper is the parent element and nickel is the uh, impurity. So therefore the impurities varies from 0 to 100. Okay, along from left to right. Now, okay. during cooling, how the copper nickel alloying system or copper nickel isomorphous phase system, how it changes with respect to cooling the systems. Okay, now at very high temperature, at very high, for example, we can take for 35. So for this specific composition range, 35 means 65 percentage of copper plus 35 percentage of nickel will present there. Okay, so at the specific composition range, at very high temperature, that means 1400 degrees Celsius, 1400 degree or 1000 above 4400 degrees Celsius, the given alloying system exhibit liquid state. Liquid state. So when we reduce the surrounding temperature or when we reduce the temperature due to reduction of temperature, so the nickel atoms are start to solidize. So therefore, solidification starts after the liquidous region. After liquidous boundary, the solidification starts. Solidification. So therefore, the nickel atoms are initiate the solidification. So therefore, solidification started, and then and it is completely solidified after the solidus boundaries. After the solidus boundary. So therefore, the given alloy system for a specific range, that means for a specific composition range, the given alloying system or isomorphous system exhibit three different stages for this 1450 degrees Celsius, 1450 degree Celsius, the given alloy system exhibit liquid state, and then when we cool it or when we reduce the temperature, its solidification started. So that between this two boundary region or L plus alpha region, the solidification will be slowly increases, and after the solidus boundary, the given system is completely soluble or is completely solidified. Solidified. Next one. Okay. So the microstructure study is very useful to to find out the diffusion of the impurity atoms within the alloy system is easily studied by the microstructural studies. Okay, the microstructural studies is used to determine the how the atoms are completely present within the in liquid state or solids in both the stated both in both the state, how the atoms are arranged. Okay, within this alliance system for a specific composition value, that means 35. So 35 is nothing but 35 is the this 35 represent the amount of nickel. Okay, so the copper is varies from 100 to 0. Okay, the copper varies from 100 to 100 to 0, and nickel varies from 0 to 100. Okay, so for a specific range or a specific for a particular or specific composition value, how the alloying system exhibit how it is exhibit a diffusion of atoms for a specific is easily represented by the microstructural studies. Okay. Okay. So again, So small glance about the today's lecture. So isomorphous the phase diagram is nothing but the phase diagram. It is the graphical representation of the substance under the different environmental conditions such as pressure and temperature. So depend upon the pressure and temperature how the substance varies. Okay, it is easily represented by the phase diagrams. Okay, the phase diagram has been classified in several ways: a unary phase diagram, a binary phase diagram, and a ternary phase diagrams. So this classification is based on the amount of substance or amount of element present within the substances or present within the aligned system. Okay, uh, in our syllabus we are going to talk about the binary phase diagram. So binary phase diagram nothing but the given substance or given components has two elements. So these two elements we can change the composition values. We can change the composition values of these two components, how it varies. So how it varies with respect to the temperature has been studied by this binary phase diagram. So binary phase diagram has several ways or several numbers. Okay. So one of the important binary phase diagram is isomorphous phase diagram. Okay. So in isomorphous phase diagram, the given two components are completely soluble. Okay. Uh, so in this isomorphous phase diagram, the two components are completely soluble, and then the two components having the same crystalline structure. So therefore, easily soluble within the range. So within this, okay. Now, in isomorphous phase diagram, the important example for isomorphous phase diagram is a copper nickel phase diagram and a, gold and a silver phase diagram. Okay. So in isomorphous phase diagram, in copper nickel phase diagram is the example for substitution of solid solution. So copper and nickel has the same crystalline structure. So therefore nickel and then copper and nickel has the same size of the atoms, the same or similar size of the atom. So therefore the nickel replaces the copper atom. So therefore it occupies the copper atom. And then next one is in this isomorphous phase diagram, pure copper has the melting point temperature is 1085 degrees Celsius. 1085 degrees Celsius. When we change the composition of a nickel from 0 to 100, the melting point temperatures is varies from 1085 degrees Celsius to 1004, and finally it is reached at 1483 degrees Celsius. Okay. Between these compositions, the atoms are completely soluble in liquid, solid, and liquid state, solid state, and two-phase regions. Okay. Okay. For example, this is there's a magnification region in the within the copper nickel phase diagram. Okay. So when we change the composition, the melting point temperature is slowly raised, and then the width of the two-phase region is also increased due to the different composition. Different composition. So um, in isomorphous phase diagram, it has three different phases. One is the liquid, and two-phase region and solid. Okay. So in liquid, all the atoms are in liquid state. Okay, and then in solid state, all the copper and nickel atoms are exist in the solid state. Okay, between the two boundary state, that means within the two boundaries, that means between the region liquidus and solidus, it is called as two-phase region. Within this region, how much amount of solid and how much amount of liquid is exist will be calculated by using the tie line under lever rules. Tie line under lever rule. Okay, we can tie line is nothing but we can draw a horizontal line between the boundaries for a specific temperature. Okay, so therefore these isothermal line intersect two opposite boundaries, and then we can draw a vertical. So these horizontal line intersect the two opposite boundaries, and then After that, we can draw a horizontal vertical line from the boundary region to the composition axis. So therefore, the line drawn from the liquidous region is called as liquid composition, and solid boundary is called a solid composition. And using lever condition, we can draw a middle line. So this middle line is defects or represent the equilibrium condition. So therefore, at the CO, that is called as that value is called as CO, overall composition. Using these values, we can find out the amount of phases present within the specific temperature within the two phase boundary regions, and then the degrees of freedom within the single phase region and the two phase region is also calculated by using the Gibbs phase rule. Okay, is the Gibbs phase rule. F is equal to C minus P plus 1. Okay, C is called as a composition and P is the number of phases. Okay, so using this rule, we can find out the degrees of freedom for the particular composition values. Okay, so, so next one is the microstructure studies, how the atoms are diffused within the alloying system has been studied by the microstructural changes during coolings. Okay, in isomorphous phase diagram, both are having the same crystalline structure, so therefore it exists or evenly distributed with or evenly diffused within the alloying systems. Okay, thank you.